catering.
If you realize start afternoon session, let me introduce myself first. My name is Péter Makra, and I'm going to give you a talk which I'm very much afraid of, because half of you, although it might not be true at the moment, half of you are physicists, half of you are medical people, and I'm going to, my task is to give you a talk on fundamentals of optics, which will be too boring to physicists and too superficial to medical people. I can't really resolve this contradiction, so I should like to ask you to bear with me. Okay, so you can see the outline of this talk. I'm going to tell you about geometric optics and some wave properties of light. Then, in view of the laboratory practicals you are expected to do at the end of this summer school, I focused on two special areas: Fourier transform you might need, and frequency doubling you will do. Okay, so we are going to talk about, this summer school is about lasers. Lasers is a special form of light. I'm not going to tell you about in what ways it is special. You will hear about it. So I'm going to talk about light, which is a very strange entity. From the very beginning, there has been a debate whether it's a particle or a wave. It was strange that Newton, who thought it to be a stream of particles, were much closer to our current wave view than his opponent argues, who proposed a wave view. And then it has been established with the work of Maxwell, Faraday and Maxwell, that electromagnetic waves must exist, and light, we know, is representative of these electromagnetic waves. And then another strange twist in the story in the 20th century, that we have found, quantum mechanics have found a multitude of phenomena in which light does behave as a particle, in the sense that it can only exchange energy with matter in discrete, well-defined packets tied to its frequency. Okay, so I'm going to start with a ray model of light, a ray model that assumes that light propagates in a straight line unless the optical properties of the medium around it, or in which it travels, change, or unless it arrives at an interface between two media. When it does, when the optical properties change, or it arrives at an interface between media, it will change direction, but not in any other way. So this ray model of light builds up approximation, an application of optics called geometric optics, and these ways representing the light waves are basically lines in the direction in which a wave propagates, lines that are perpendicular to wavefronts, as you can see in this figure. Okay, so wavefronts are a collection of points in space in which the wave is in the same state, so everywhere there are crests or troughs or somewhere in between. So the important thing is that it's in the same state, and with rays are lines perpendicular to the wavefront. Okay, so in this approximation, the two basic things we should consider are reflection and refraction. So whenever light arrives at a boundary between two media, part of it will be reflected from the interface, and part of it will enter the new medium. And it is true that if we take the normal on the surface at a point where the light ray is incident, it's true that the incident ray, the reflected ray, and the refracted ray are in the same plane. That is one of the observations. And then what concerns reflection, and if you allow me, I in addition to these being in the same plane, that the angle of incidence is equal to the angle of reflection. Okay, what about the part that enters a new medium? It's not that easy. It depends on the media. It will change direction, as you can see in the figure. Here we have light traveling from an optically denser medium to an optically less dense medium. So here light travels slower, here light travels faster. In this case, the angle of refraction, now I try to pronounce the difference between reflection and refraction, will be greater than the angle of incidence. How much greater? It is determined by the law of refraction, or Snell's law, which states that the sine of the angle of refraction divided by the sine of the angle of incidence is equal to the ratios of wave speeds in general, or light speeds if we talk about light, in the two media. It's convenient to define the index of refraction, which is the ratio of the speed of the wave in the reference medium. If we talk about light, the reference medium is vacuum, so the speed of light is vacuum, divided by the speed of light in the given medium. So naturally, because the speed of light is greatest in vacuum, it's a number greater than 1. It's just a number, so it has no limits. Sometimes it's also convenient to define a relative refractive index of two media. Relative refractive index of medium 1 with respect to medium 2 is the ratio of these two refractive indices. Okay, and using these refractive indices, we can rearrange Snell's law and have it in different form. You can see few sample values of refractive indices as far as I could get it. When speaking about refraction, one has to consider the phenomenon of dispersion. Dispersion means that the refractive index of light for a given medium is not a constant value. It does depend on the wavelength of light. So for different colors, refractive indices are different. Therefore, if the refractive indices are different, angles of refraction will be different, meaning different paths for different colors in the medium. This is how white light, which is a mixture of colors, now we know that it's a mixture of colors, can be broken down into component colors, which component colors cannot be separated further. So if we pass them through a medium again, they will not be broken down further. This is how Newton proved that this is indeed, so white light is indeed a mixture of different colors, and it's not the case that the prism or the glass does something to the light and this changes the properties of light, but instead it's a mixture. Such a device in which we can observe dispersion is called a dispersive element, for example, prism. You can see the prism here, and a famous prism here. Most famous, I don't think it's the best of them, but it's the highest rank as far as I know. Okay, still not leaving refraction, a very important phenomenon can be observed when light travels from an optically denser medium, that is from a medium in which the speed of light is less, into an optically less dense medium in which light travels faster. In this case, as we have seen, the angle of refraction will be greater than the angle of incidence. And we might reach an angle of incidence to which an angle of refraction of 90 degrees would belong, which will not happen. So this is the critical case. This is the critical angle to which the angle of incidence to which an angle of refraction of 90 degrees would belong is called the critical angle. And when the angle of incidence reaches the critical angle, no refraction will occur. the incident light will be totally reflected, everything will stay inside, all the intensity of the light will stay inside the original medium. And the reason why it's important is that it has its practical applications. If you substitute the values into Snell's law, Snell's equation, you can see that the angle of refraction is 90 degrees, whose sine is 1, so the equation is really simple if we want to obtain the critical angle for 2 medium. Okay, and a few examples. When from below the surface of water, we look outside, the surface of water looks somewhat like a mirror, and an even more important application, and I think I didn't have to interact with it here. Sorry about it. So, a very important application is the optical fiber. An optical fiber is a fiber from which the light cannot leave. It's very thin, so these angles of incidence are consequently high, and they are always above the critical angle, so all light is bounding between the walls but cannot leave the optical fiber, which is favourable to us. This way we can use the optical fiber to conduct light from one place to another, and it can even be curved, and here you can see a model, so this is not an optical fiber, it's a glass rod, it illustrates the principle. So, out of curiosity, let's take a look at how much, how it depends on the properties of the optical fiber, the angle or the radius to which we can bend it. So the question is, if we have an optical fiber of thickness d and a refractive index n, what is the smallest radius of curvature to which we can bend this optical fiber? And if you consider that this innermost ray has the smallest angle of incidence, therefore the greatest chance of escaping, then you can see that we need to consider only this ray, and for this ray we can use geometrical considerations. Here we have a right angled triangle with r minus d, d is the thickness of the optical fiber, as the side opposite this minimum angle, and then we have the radius of curvature as the hypotenuse. Using these, we can calculate the sine of this minimum angle. If this angle is greater than, if the sine of this angle is greater than the sine of the critical angle, then no light will escape. So this is a boundary condition. If we rearrange that, we get that the radius must be greater than dn over n minus 1. In this equation we use the refractive index of air as approximately as 1. And if you rearrange this equation, you can see it's d over 1 minus n, which means that the thinner your fiber, the less the radius, so the more that you can bend the fiber, and the greater the index of refraction. 1 over n is less, 1 minus 1 over n is greater, so 1 over 1 minus 1 over n is less than, so r will be less, it means bend will be, so it can be bent more in less radius than before, so this is desirable. Okay, that's about optical fibers. And now let's move on to the image formation of optical devices, simple optical devices such as mirrors and lenses. So in this, still within the rainbow of light, so we will not consider any deviation from the rainbow. We still assume that light rays in the medium travel in a straight freeform region or into the interface between two media. So within this approximation, we will consider the effect of optical devices and light rays in a framework that we have objects. These objects, the light rays from these objects, pass through or reach optical devices because they will not pass through the mirror, for example. And as a result of either refraction or reflection on the optical device, new light rays will reach our eyes and we will see an image. And the task is to find the image itself and the properties of the image. So, before going on, let's discuss two important concepts. How do we find an image? We see an image, simply speaking, that when light rays diverging, so spreading out from a point, if we talk about a point, from a point to reach our eyes, and if these light rays indeed diverge from that point, so these light rays have travelled on from that point, we talk about a real image. Real images are images which can be like this, projected on the screen. And if it's not true, light rays only appear to diverge from that point, we call the image virtual image. Okay, we define the distance from the object, distance of the object from the optical device, the distance of the image from the optical device, BQ are limitations, the perpendicular size of the object and the size of the image, perpendicular to the axis of the mirror or the axis of the lens, and the linear magnification, which is the image size divided by the object size. And the simplest optical device based on the physical phenomenon of reflection is a plane mirror, and this serves as an example of how an image can be constructed. So here we have a point O. So point O here. The light rays coming from that point, obeying the law of reflection, are reflected from the surface of the mirror, form divergent rays, and our eyes can't distinguish these divergent rays from rays that originally came from this point. They seem to diverge from this point I, and therefore I will be the image of this point O. And as we have discussed, these rays have never been behind the mirror, so these rays do not diverge from this point, they just seem to diverge, therefore this is a virtual image. It cannot, so if you stand with let's say, a sheet of paper in front of the mirror, your mirror image will not be projected on the sheet of paper. Okay, so for a plane mirror, simple geometrical considerations allow us to find that the image distance is equal to the object distance in absolute value. We are going to discuss why do we have to put a modulus here. Then the image size is equal to the object size. The magnification is equal, by definition, to the image size divided by the object size. Minus the object size divided by minus the image distance divided by the object distance. In this case, this is 1. Okay, the reasons for this minus are to be discussed. But I wanted to do it once, and before getting there, let's see slightly different mirrors, spherical mirrors. Spherical mirrors are mirrors whose surface has been cut, or they have geometrical properties as if their surface has been cut from the surface of a sphere. And then you can identify some important points here. The center of the sphere from which they were cut is the center of curvature. The geometrical center of the mirror itself is called the vertex, and halfway between the center of curvature and the vertex we have the focus. Focus means hearth or fireplace in Latin, so this is a place where light, for a concave for mirrors and lenses, what I'm going to tell you is not strictly valid. So if you try to solve the equations, do the geometry, it will not always match. Only for in an approximation, in a circle paraxial approximation, which uses rays that travel close to the principal axis and make a small angle with the principal axis. Technically, the small angle is less than 5 degrees, in which case you can approximate trigonometric functions like the sine with the angle itself expressed in radians. I was just curious how well it works. And what you can see here is I tried out the difference, plotting simply an angle, the value of an angle in radians, the sine, and you can see that with this we are too straight. So up to, let's say, 15 degrees, the difference is not noticeable. So it indeed seems a good approximation sometimes. And for these paraxial rays, we can define a set of principal rays which help us find the image for a mirror. For a concave mirror, I haven't told you about the difference between a concave mirror and a convex mirror. The difference is simple. Where is the reflective surface? For a concave mirror, the reflective surface is the hollow side. I hope I'm right. So concave and the hollow side is the reflective surface, and for a convex mirror, the bulging side is the reflective surface. And for a concave mirror, you can find the principal rays. The first of these is a ray that travels parallel to the principal axis. These rays are reflected so that they will pass through the focus. So this is the first. Then rays passing through the focus, I hope I keep the numbering, yes. So rays passing through the focus will be reflected parallel to the principal axis. If a ray is incident at the vertex, it just obeys the law of reflection, so this angle will be equal to this angle. And if a ray passes through the center, because the angle of incidence is 0 in this case, it will be reflected in the same line. Okay, so using these principal rays, you can find the image of an object. For example, here is the object. Here I have used 3 rays, but 2 are enough to find an image of the point. For example, the first principal ray can be applied. The second principal ray can be applied. They cross at this point, so the light rays coming from the image seem and do diverge from this point. So this point I is the image of this object. The third one is just an extra. In this case, we do not really need it. Okay, now it's time to talk about a few sign conventions which explain why I use a negative sign in magnification of a plane mirror. So in order to be consistent in our equations, we introduce some sign conventions. For example, the object location, object distance can be positive or negative. Image location can be positive, negative. Height, magnification, focal length can be positive or negative. A positive object location is for an object in front of the mirror, object in back of the mirror. A virtual object has negative object distance. Image in front of the mirror, a real image, has positive image location, image distance. In back of the mirror, it's virtual. So in the plane mirror example, we have a negative image distance. So to get a positive magnification, we need a negative sign. Why does the magnification have to be positive? Because the convention is that an upright image has a positive image height and positive magnification, whereas inverted images have negative image heights and magnifications. And for focal length, concave mirrors have positive focal lengths, convex mirrors have negative focal lengths. Using geometrical the third. And then you have an inverse relationship. So the inverse of the focal length is equal to the inverse of the object distance plus the inverse of the image distance. If you use the proper, so if you use the conventions right, this will be consistent and will tell you the properties of the image or the object, whatever you are looking for. Depending on where you put the object in front of a concave mirror, the properties of the image can be different, so we can have real images produced by concave mirrors. In 3 cases, whenever we are outside the focal distance and have a virtual image when the object is inside the focal length, if we, theoretically speaking, if we place an object into the focus, no image will be generated because divergent rays will be reflected, parallel rays never meet. Okay. As for the convex mirror, this is like left or right, east and west, concave and convex. I keep interchanging them, that's why I have to concentrate. So for a convex mirror, these are the principal rays. The parallel ray will be reflected so that its extension passes through the focal point. A ray whose extension passes through the focal point will be parallel to the principal axis. The vertex incident rays will obey, just like any other rays, will obey the local reflection. So this angle here with the principal axis will be equal to this angle here with the principal axis. And rays which target the center of curvature will be reflected back to themselves. Convex mirrors are easier because in the case of convex mirror, the image is always virtual, it's always applied, and it's always reduced. You can find the image of a convex mirror using 2 of these principal rays. Here I only use 2 because I couldn't match a third. So I made this figure, and however I tried, the third one didn't want to meet here with the others, so I omitted it. So 2 principal rays are enough, and using, for example, the first and the fourth, we can find an image that is behind the mirror, so it must be virtual and upright and reduced. And this is the end of the part about mirrors. Mirrors are optical, in summary, are optical devices that use reflection to produce images, but you can also utilize refraction to produce images. So for example, here, if you have a curved surface of medium with different index of refraction, different from the surrounding medium, you can see that in this case, when the refractive index of the medium is less than that of the environment, the angle of refraction will be less than the angle of incidence. So divergent rays will be made convergent and will meet at this point. And this is the basis of lenses. Lenses contain at least 1 curved surface, and the surfaces can be in several different arrangements, so we can have a multitude of lens types. There's 2 basic types. With respect to their behavior, are converging and diverging lenses. Converging lenses collect parallel rays into their focus or foci, whereas diverging rays make parallel rays divergent. Okay, and because this is based on refraction, so light can travel in both directions, we need focal points on both sides. So the case is not as easy here as with spherical mirrors. It's not automatic that the focus is located at half the radius of curvature. We are going to see how to find the focus, but it's important to know that there are focuses for foci on both sides. And it's a very economic situation because we can use a mirror equation close to the same as that for mirrors. If we have lens systems of thin lenses, now for lenses it's important that there can be thin lenses and thick lenses, and these laws are valid to thin lenses. Thin lenses are lenses whose thickness is negligible as compared to the radius of curvature. And if the lens is thick, this description is not sufficient. I'm not going into thick lens descriptions. And if you have a lens system of these thin lenses placed close to each other, just like the situation in objectives, camera objectives, or basically everywhere in every optical device, there is a need to have complex lens systems. And if they are thin lenses placed close to each other, the inverses of their focal lengths will be added together. And if you think about lenses like glasses, it's unlikely, as you know, the focal length of the glasses you wear, but the optical power is much more familiar. When you buy glasses, it's more likely the optical power that is specified. The optical power is the inverse of the focal length. The optical power is expressed in diopters, and in lens systems, the optical powers are just added as we have seen. Okay, so as I've told you, the lens equation only works if you are strict with your conventions, and the conventions are similar to those of mirrors. The difference is, for example, the image. If the image is if the image was in the back of the mirror, we called it a virtual image, and the sign, or the negative sign to it, is the opposite. The real images are in the simple situation, because you can have more complex situations in the system, but in a simple situation, the real images are in the back of the lens, having a positive image distance, and virtual images are in front of the lens. The rest is the same. The radius of curvature has to be assigned positive and negative sign as well. So if, when viewed from the direction from which the light comes, if the center of curvature is in the back of the lens, we have a positive radius of curvature, and when the center of curvature viewed from the direction from which the light comes is in front of the lens, we have a negative radius of curvature. Focal length is positive for converging lenses. Lenses is negative for diverging lenses. And let's see the principal rays for converging lenses. Three principal rays. The one traveling parallel to this one traveling parallel to the principal axis will be refracted so that it will pass through the opposite focal point. Then a ray that comes from the object side focal point will be refracted so that it will be parallel to the principal axis. And if the ray, a paraxial ray, passes through the center, the geometrical center of the lens, it will not change direction. Depending on where you put the object, the image can have different properties. If the object is outside, twice the focal length so outside, twice the focal length, we will have a real image, which is inverted and reduced. If we are between the focal distance and twice the focal distance, the image will still be real, still be inverted, will be magnified. And this is the magnifying glass situation when the object is placed within the focal distance. In this case, using these principal rays, we can see that we will have a virtual image. So these divergent rays have never been here. They just seem to diverge from here. So this is a virtual image. Okay, this is a table summarizing all the different probabilities. Again, if we place the object into the focal point, theoretically for paraxial rays, we will not have an image because all the rays diverging from the diffuse and upright and virtual images, the principal rays for them that are the following. A ray traveling parallel to the principal axis will be refracted so that its extension will pass through the same side of the ray. Then we still have the principal ray passing through the geometrical center will continue on in the same line, and an incident ray whose extension passes through the focal point, which is the incident ray whose extension passes through the opposite side focal point will be refracted so that it will travel on parallel to this axis. Okay. As I mentioned, the focal distance is not a simple function of the geometrical properties as for spherical mirrors. In order to find the focal length of a lens, we must consider all the refractions that occur at lens surfaces, at these two surfaces. And if the case is that we have the same medium on the two sides of the lens, we find the so-called lens-maker equation, which allows us to find the optical power if we know the parameters of geometrical parameters of the lens, namely the radius of curvature of one of the surfaces and the other. And here you can see this is the English convention in which we have a negative sign, taking into account that the other, for example, for a symmetrical lens, the other surface will have negative radius of curvature. So even for a symmetrical lens, it will not vanish. Instead, it will reduce R over 2, or 2 over R. Medically, an important case when you don't have the same medium on the two sides of the lens. For example, we have here the front of our eye and the aqueous or vitreous humor on the other side. And in this case, we don't have a single focal length, but we have an object side focal length and image side focal length. Instead of these, I just use the object distance and image distance, and you can find the relationship between these and the geometrical